We have been working with the two body problem. So, we continue with that. So, in that context today we will be taking up the orbit determination problem of a satellite from the burnout data. So, what happens, we intend to put the satellite in some orbit, but in reality it is never possible to put the satellite in the same orbit in which we intend, because of the under or the over functioning of the rockets. So, today we will look into that if the satellite is injected into the orbit. So, at that time the inertial navigation system, it will transmit the initial position and the velocity vector of the satellite, and from there we can know in what orbit the satellite is. But over a period of time, then what is called the preliminary orbit determination. So, in the preliminary orbit determination, using the first few minutes data, again the orbit determination is done to make the orbit parameters very precise, so that the tracking can be done properly over a period of time. But burnout data itself, it gives you enough information, so that you can adjust the radar and you can point it in a particular direction in the sky, so that the tracking will continue before the preliminary orbit determination data is available. So, to start with, we have the condition that given r 0 and v 0, that is the position and velocity vector of the satellite, which is available from inertial navigation system INS. So, using these informations, what we need to find out is the semi major x, E the small eccentric, this is called the eccentricity, this is the angle of inclination or the orbit inclination, capital omega, this is the nodal angle, small omega, this is called the argument of Parisi, and theta, this is the true anomaly. So, these 6 parameters together they characterize the orbit completely. Okay. So, instead of using r 0 v 0, you can use them to characterize any orbit. So, it characterizes any orbit completely. And today we are going to work out how to get these quantities from r 0 v 0, which is given to us. Now, let us consider the earth is given, okay, and somewhere on the earth you are launching the satellite, say from this position somebody has launched the satellite. So, satellite will go like this through the, so rocket will be launched and then ultimately it will be putting it in a orbit. So, here the rocket will come and it will inject into the orbit with certain velocity v 0. We draw a radius vector from this point to this point. So, this is r 0, the radius vector at burnout. So, this is your burnout position, This is the angle theta. So, let us say the orbit in which it has been injected, that orbit it looks like somewhat like this, and this is the Parisi position. Okay, so, if this velocity vector is broken in along the two directions, and this angle which is beta, this is called the flight path angle, flight path angle, and this angle, the other one, this is alpha. Okay. Sometimes, so the flight path angle is measured from the local vertical, local horizontal. So, this is your local horizontal, local horizontal. So, from here the flight path angle is measured and the angle alpha is shown here. Sometimes it is a, many of the literature may be mentioning the alpha angle from this horizontal line to the toward the velocity vector. Okay. So, your radius vector is in this direction and velocity vector is in this direction. So, using these informations, now work out the initial orbit of the satellite. As you may be aware of that in the inertial reference frame, we have been showing the orbit like this. So, this is the orbit, this is the nodal line n prime m n, and somewhere this is the perigee position. This angle is argument of perigee. Satellite is, say, it is here satellite, then this angle is theta, which is the true anomaly, and the angle the satellite makes with the x y plane. So, here this angle that it makes with the x y plane, this is the angle of inclination, angle of inclination. So, we have discussed earlier these points. So, the figure we are taking right now is this, it is the orbit which is lying above the x y plane. So, this orbit will go down and you can complete it by showing it by the dotted line which is lying below the x y plane. So, you take this whole orbit and in this orbit you can show it in this way. So, you have launched the satellite, satellite is injected at this point. So, at the time of injection the velocity is v 0 and the radius vector is r 0. So, r 0 implies you are given in the inertial reference frame, say we can write x 0 I cap times y 0 j cap plus z 0 k cap, where I 0 I, j and k cap, these are the unit vectors along the x, y and z directions. Similarly, v 0 we can write as this, we can indicate by the components wise x dot 0 I cap plus y dot 0 j cap plus z dot 0 k cap. Now, in the previous figure that we have taken, now leaving out the launching position, only we are concerned with the velocity and position vector right now, and this is, say, the velocity vector v 0. This angle we are writing as beta and this angle we are writing as alpha. So, from here you can see that this v 0 vector, it can be broken in this direction as v 0 cos alpha, and in this direction its a component will be v 0 sin alpha. So, we are writing in terms of alpha. So, same way you can also write in terms of beta, it is not a problem, or as I told you that many times it happens that the alpha angle is described from this blue line which I am extending, this is called the local horizontal. So, it is measured from here to here sometimes. So, either way if you write this alpha you measure from here or either from here, it does not matter, it will just alter your equation, but you can always get back to another equation by choosing different values of the alpha, either this one or this one. So, it is always possible to modify it, and this angle we have indicated as theta. So, we have V r is equal to r dot, which is the radial component. We are writing this as the V 0 cos alpha, and the theta component, which is perpendicular to the radius vector in this direction. So, this is your V r and this is V theta, and this will be r times theta dot, and we have already done this problems. Y B theta will be equal to r times theta dot. So, this is V 0 sin alpha. Also, we know that L by r is equal to 1 plus E cos theta. So, this is the equation of the conic section. This is equation number 2, equation number 3. Now, the angular momentum of this satellite, this we can write as h equal to h magnitude is equal to h is equal to r 0 cross v 0, and this is per unit mass. Okay, angular momentum per unit mass. Here nowhere m is appearing. So, this is basically your r 0 v 0, and the angle between r 0 and v 0 is alpha here. So, we write here sin alpha. So, this is equation number 4. Similarly, we can write r 0 dot v 0. Okay. So, this we can write as r 0 v 0. The angle between these two is now cos alpha. Here the angle is alpha. So, therefore, this will be cos alpha, and r 0 v 0, if you take the dot product of these two. So, here we can write on the from this equation cos alpha, this is equal to r 0 v 0, taking the dot product, this will be x 0 times x 0 dot plus y 0 times y 0 dot plus z 0 times z 0 dot divided by r 0 v 0, and this is our equation number 5. So, these are the preliminaries that we are building to solve the equations further. Now, the first equation that we have written, L by r is equal to 1 plus cos theta, 1 plus E cos theta. So, differentiate that. So, differentiating equation 1, this will yield L by the left hand side L by r square times r dot is equal to minus the right hand side minus C sin theta times theta dot. Okay. So, you can simplify it little bit further, and we can write E sin theta is equal to L r dot by r square theta dot, and you know that theta dot you are aware of from the previous discussion. We know that r square theta dot, this is nothing but h. So, theta dot becomes h by r square. Or here, so this quantity you can pick up from this place. We have taken here this one L times r theta dot r square times theta dot. So, directly we can write here the h from this place. Okay. Either taking this or either taking this, you get this equation. So, this is L times r dot by h. Now, h also you know from our previous working the earlier lectures that h is equal to mu L under root, that is h square is equal to mu times L. So, therefore, this implies E sin theta, this is equal to L, we can replace from here h square by mu and then r dot divided by h. So, this is h r dot divided by mu, and h we know how much this is r 0 v 0 sin alpha, and r dot nothing but v 0 cos alpha and divided by mu. So, this gives you E sin theta is equal to r 0 v 0 square sin alpha times cos alpha divided by mu, and this is our equation number 6. Okay. Now, E cos theta you can write as, using the equation number 1, E cos theta from here L by r minus 1, L by r minus 1, and L already we have written here L equal to h square by mu, and h we know this quantity is r 0 v 0 sin alpha. So, this is r 0 v 0 square sin square alpha divided by mu times r. Now, we are replacing with r 0 minus 1. So, this gives you E cos theta, this is equal to, okay, we will keep it in the same form. So, let us write this equation is the equation number 7. Using equations 6 and 7, we can write tan theta equal to sin theta by cos theta. Okay, E sin theta by E cos theta is equal to tan theta. E gets cancelled out, and this quantity. So, we are using this equation number 6 and equation number 7 here. So, r 0 v 0 square sin alpha cos alpha divided by mu times 1 by r 0 v 0 square sin square alpha by mu times r 0 minus 1. So, if we write A is equal to r 0 v 0 square sin alpha, then this equation gets reduced to tan theta, this is equal to A cos alpha divided by here h square, this is square term we are missing. So, we supplement that. Mu r 0 is here and this is r 0 square here in this place. So, this must be supplemented. So, here after cutting it you can write it that r 0 v 0 square sin square alpha. So, this will become A times sin alpha minus 1, and this is our equation number 8. Okay. So, this gives you tan theta. Now, theta we have done. So, now we work for A, the semi major axis. So, we know from our earlier lectures that the specific energy of the satellite, that is the energy per unit mass, this is nothing but mu by minus mu by 2 A. Okay. And this we have written as V square by 2 minus mu by r. So, this you can rearrange and get A from this place. So, what we can do, after rearranging, we can write here A equal to R 0 by 2 minus V 0 square by R 0 mu. So, this is just the rearrangement of this is required. We are interested in this quantity. So, we will put it in this way. We will write A equal to minus mu by 2 divided by B square by 2 minus mu by R. Okay. And if you rearrange it here, so this is mu by 2 times minus sign we will take inside. So, this will become 1 by mu by R minus V square by 2. Okay. And if you take R from common from here, so this will become mu by 2 times R 0. So, R I am taking common from the denominator here of the lower portion of the denominator from the this denominator portion, whole denominator portion. So, this becomes, and mu also we can take it outside. So, here what we get 1 minus V square by R we are taking outside. So, R will go on this side and mu will appear here and 2 remains here in this place. So, this mu cancels out, what we get here R 0, 2 we can take inside. So, this becomes 2 minus V square by R by mu. This is your A. Now, finally, this R and V need to be replaced by R 0 V 0. So, we get this equation, and this is our equation number 9. So, this is the equation for the semi major axis. So, we have calculated till now theta and A. Now, we need to work out further. Okay, eccentricity, next we are going to work out the eccentricity. And this we are all doing from the burnout data. So, again looking back into our equations, the equation 6 and 7, this is written in terms of E sin theta, E cos theta. On the right hand side, you can see that R 0 V 0 is known to us, and therefore, alpha will be known to us, because the direction is given for the R 0 V 0, mu is known to us. So, right hand side is known to us, and therefore, the left hand side if we square and add, so we get the eccentricity. So, here E square, this becomes E square sin square theta plus, so here we write squaring equation 6 and 7 and adding E square cos square theta. Okay, so, this becomes R 0 V 0 square sin alpha cos alpha by mu whole square plus R 0 V 0 square sin square alpha by mu so for R 0s, here one thing what we have missed out, and that we need to supplement this while writing tan theta is equal to E sin theta by E cos theta. So, we wrote this equation. Now, r 0 v 0 square sin alpha cos alpha and this is mu. Here this term already we cancelled, r square term was there. So, this cancelled. So, this term is not present here. So, this correction must be given and then what we will do here, we will put the mu in the denominator of this. So, A equal to r 0 v 0 square sin alpha by mu and then you write this. So, then it becomes A cos alpha, this term becomes A and then the cos alpha, and here also you can look into this, here you will get A times sin alpha minus 1, then it becomes correct, otherwise this term was missing here. So, we are supplementing it here and take this as a correction. So, A is your r 0 v 0 square sin alpha divided by mu, and this is the correction provided here. Okay, so, we have here r 0 v 0 sin square alpha and divided by mu, this is the quantity we are taking, r 0 v 0 square sin square alpha divided by mu minus 1 and then whole square. So, expanding it, cos square alpha divided by mu square plus r 0 square b 0 to the power 4 sin to the power 4 by mu square, okay, minus 2 times r 0 v 0 square sin square alpha divided by mu plus 1. Now, here from you can take sin square alpha r 0 square and v 0 to the power 4 as common, and we can write here r 0 square v 0 to the power 4 sin square alpha, taking this as common and mu square in the denominator. So, after taking common we write this as cos square alpha sin square alpha minus 2 r 0 v 0 square sin square alpha divided by mu plus 1. So, this gets reduced to r 0 square v 0 to the power 4 sin square alpha divided by mu square minus 2 r 0 v 0 square sin square alpha divided by mu plus 1, and this is your E square. So, this gives you the value of E, and this is the equation number 9. So, thus we see that till now we have worked out the theta, the semi major axis and the eccentricity. So, these three quantities are worked out. Next, we will try to find out now if what is remaining, our I, small omega and capital omega. So, this we need to work out. Also, we can recall from our earlier discussion that is in the earlier lectures we have worked out this, and we have written there v square by 2 minus mu by r. So, this quantity is nothing but E square minus 1 times mu square by 2 h square, and you can verify, you can check this. This is E square minus 1 and mu square, h square is nothing but mu times L. So, this is mu times L, and again you can replace. So, this mu will cancel out and you get here 2, and L is A times 1 minus E square. So, once you cancel it out, so this quantity cancels out and leaving you minus mu by 2 a. So, this is what you have written as E prime equal to V a square. This is the kinetic energy per unit mass and this term is the potential energy per unit mass. So, this is the total energy per unit mass and this is minus mu by 2 a. Therefore, we can write here E a square minus 1. From this equation we can write E a square minus 1 equal to 2 h a square by mu a square. We are using this equation times V a square by 2 minus mu by r, and this implies E a square is equal to 1 plus 2 h square by mu a square times V a square by 2 minus mu by r. So, now h is known to us, this quantity is known, mu is known, V you can replace now by V 0 and r can be replaced by r 0. So, also you can get eccentricity directly in terms of this equation. So, we have two equations for finding out the eccentricity, either we use this or either we can use this. This is 9.6, this is 9.7. Okay, once we have done this, now we go to the next step. This tan alpha is a quantity that we can write as 1 plus E cos theta by E sin theta, and this equation is very useful and quite frequently used, and you can prove it very easily. Tan alpha in fact you can write as V theta by V r. Just look into the previous figure that we have drawn. Okay. So, from here V theta is nothing but r times theta dot and V r is r dot. So, theta dot you can replace in terms of h. So, this becomes h by r times r dot. Now, h you can replace in terms of mu l. So, this is mu l under root, where l is the semi lattice rectum, and r you can write as l by 1 plus E cos theta, and r dot obviously we need to replace here. So, you recall from our earlier discussion how much r dot is. So, look into this equation. This r dot you can write from here mu times E sin theta divided by h. So, here r dot is appearing. So, we can write mu times E sin theta and this divided by h. Now, this need to be simplified little bit. So, what we will get from here 1 plus E cos theta divided by E sin theta, and this times rest other things we have to bring in one place, mu l under root, and this is divided by L, and from here we get h in the numerator and this gives us mu in the denominator. So, we can write here tan alpha equal to 1 plus E cos theta by E sin theta times Now, mu L under root is nothing but h square. So, this quantity mu L under root is nothing but h square. So, we take the under root of this is h, and again in the denominator you have the mu times L, which is nothing but h square. So, this will cancel out, leaving you with 1 plus E cos theta by E sin theta. And this relation in astrodynamics it is used quite frequently. So, I have worked it out here. Okay, now we can go for working for the I small omega and capital omega, which are the remaining parameters of the orbit to be worked out. Okay, now we take an inertial reference frame indicated by x, y and z. Unit vector in these directions are k cap, I cap and j cap. This is the origin here. This is the nodal line n prime n. This is called the ascending node and this is called the descending node, and satellite is moving in this orbit. So, the orbit that it makes inclination with this x y plane, this is your angle of inclination I. This is angle I, this is your nodal angle which need to be worked out, and somewhere on this orbit your perigee position is located, and angle to this from the nodal line we are measuring, and this is your argument of perigee, and then your satellite may be located in this orbit in any other place, and this is your r vector, and here the satellite is moving. So, this is your satellite with certain velocity v 0, or maybe for generalized case you can write v, okay, and this is the perigee position. So, the angle from here to here, this also need to be worked out, and this is your true anomaly. So, these are the three angles that we are theta we have already done this because we measured theta from the perigee position in the beginning and we have worked out. So, capital omega, small omega and this I will be working. So, now we take a unit vector in this direction, in the n direction, and write this as n cap. In this direction we have already shown k. Now, perpendicular to the orbit is the angular momentum vector. We know that the angular momentum vector is perpendicular to the both radius and velocity vector. So, the radius and velocity vector they lie in the orbital plane. This discussion we have already done. So, your the angular momentum vector it will be lying here perpendicular to the plane of the orbit, and here we put h 0 or h, or similarly v equal to v 0 for the generalized case. Once we are seeing this velocity as the burnout velocity. So, this becomes v equal to v 0 and r becomes equal to r 0. So, here h 0 this is the angular momentum vector, and n cap is the unit vector in O n direction. R 0 is your radius vector. So, with this information we can work out few more things. So, let us write H 0 equal to R 0 cross V 0, and we have earlier written also this equation, but once we write it again, then the eccentricity vector, if you remember from our earlier lectures, we can write eccentricity vector is E is equal to 1 by mu times V 0 cross H 0 minus mu R 0 by R 0. Now, the unit vector, if we take the product of k and H 0. So, we take the product of the unit vector k dot or say k cross H, we have to define n. So, n is a vector which is lying in the orbital plane, but this is perpendicular to the k vector, and also H vector which is perpendicular to this orbit, and as we incline the orbit. So, it moves from here to here, and this goes from this place to this place by angle I. Okay. So, this is also your angle of inclination. So, this vector is also perpendicular to the O n vector or the n cap vector. So, we can write this as k cross H 0, k cross, we are taking the cross product of this k cross H 0, okay, and divide by the magnitude of this. So, k cross H 0 magnitude, and this it will give you the unit vector. So, this is our equation number 12. This gives the unit vector in the direction of O n. Now, the this is the nodal angle which is we are interested in finding out. So, you can also express this unit vector in terms of this nodal angle, and we can write here n cap equal to cos capital omega I cap plus sin capital omega j cap. Okay. So, this vector is available to you here, the n vector is available to you, and from here also n vector is available to you, where capital omega and capital omega we are interested in finding out. So, if we get the expression from here and compare the sin omega and capital omega here, so we will be able to find out the capital omega, okay, because this will have the components, you can break them like this, and after this you just compare the components, and that will give you the capital omega and the sin omega. Now, the capital omega, it varies from 0 to 360 degree. It will lie from 0 to 360 degree, and you will be able to okay, and it is a possible using this to, because this is the extra information available to us, that n can be described in this way also. So, therefore, it is a you can fix the in which quadrant your this nodal line is lying. This is the first quadrant, we are here we are showing x y. So, in where it is going, this where the capital omega is lying, it is less than 90 degree or more than 90 degree, but less than 180, or it is lying between the in the third quadrant or the fourth quadrant. Okay. That is possible to work out in this case. So, we can resolve the quadrant of O n, okay, in which quadrant it is lying, it can be resolved. Okay, now, once we have done for the capital omega, so we are left with the small omega and I. So, again we take help of the figure that we have shown here. I is the angle of inclination. Okay. So, h is the vector here and k is also a vector. So, if we take the dot product of k and h, so between the angle between these two vectors will be known to us. So, let us write here now finding I the angle of inclination, the orbit inclination. So, we have k cap dot h 0 cap, this is k cap magnitude, h 0 this is not cap, this is a vector, and this implies this is the of unit magnitude, and therefore, we get here h 0 cos I, and this implies cos I equal to k cap h dot k cap dot h k cap and dot product with h arrow and then divided by h 0. This is our equation number 13. Now, in this equation we know that the I here, this is your orbit which is shown here. So, say the orbit is lying in this plane. So, how your orbit inclination will vary? Say the orbit can, suppose this is the x y plane, this is the x y plane. So, the x y plane, the orbit is coinciding with the x y plane, and then it can vary. So, this is the angle of the orbit. So, it will keep on changing there, and the lower portion of this I can make a break of this and showing that this line is breaking and showing the lower portion below the x y plane, and this is up the x y plane. Okay. So, as you move it from the x y plane, this is coinciding right now with the x y plane, and this is also in the x y plane. So, it will go like this, it comes 90 degree, and once you come to 180 degree, again the orbit is in the x y plane. Okay. So, the I will vary from 0 to 180. Hence, there will be no ambiguity in finding I from this equation, because cos is uniquely determined between 0 and 180 degree. Okay. Hence, I can be uniquely determined without any ambiguity. So, we have worked out for I. Next we can work out for capital omega is already done. For I we have already done, the small omega is remaining. Now, again we take this figure, this is the argument of Pereggi. Okay. We from our earlier lecture we know that the eccentricity is a vector which is lying in this plane along the Pereggi line. Okay. OP, this is the Pereggi line. So, E vector is lying in this direction, and n vector is given to you. So, if we take the dot product of n and E, so the angle omega will be available to us. So, now n dot n cap dot E cap, this is equal to, and we indicated by a vector E So, taking the dot product of n cap with E, we write this, and this implies cos omega, this is equal to n cap dot E divided by E. This is our equation number 14. But you remember the omega, this is just deciding the position of a line, and it will vary from here to here. Okay. So, it is a total 360 degree of rotation you can give to it. So, argument of perigee in the orbital plane, if you look. So, if this is the nodal line, so from where with respect to this nodal line, where the omega will lie, either along this is the perigee here, or either down, in which direction it is a line. So, 360 degree angle is possible. Therefore, omega here is lying between 0 and 360 degree, and quadrant resolution is required. So, if E dot k this is greater than 0, then cos omega will give correct value of omega. If E dot cap less than 0, then appropriate correction must be given. So, you can see from this place, this is the vector k here along the green line, and this is the vector E. So, if you take the dot product of this, so this is basically showing the E vector, the component of the vector E along the k direction. So, it will have a positive intercept. Okay. So, in this case, so till your vector the argument of perigee, it is lying above this. So, you get this product here, this dot product, and where the intercept will come out to be positive. On the other hand, if your argument of perigee goes below the x y plane, it is going below the x y plane, then you can see that your E vector will be lying down, while the k vector is in this direction, and the intercept will come on the negative side of the k direction. So, this is k cap negative. Okay. So, in this direction, so what you are getting a negative intercept. Okay. So, therefore, it is indicating that condition that if E dot k dot product this is greater than 0, then obviously omega is lying up. If this turns out to be, this quantity turns out to be less than 0. So, this simply indicates that omega is lying below this line, and accordingly you can take the decision. Okay. Similarly, if we will have the problem with theta also, but theta can be in the same way it can be resolved. So, if you look into the, again this theta is the angle between the radius vector and the eccentricity vector. Okay. So, we can write here E dot r 0, this is equal to E magnitude times r 0 magnitude, and the angle between is cos theta. So, this implies cos theta equal to E dot r 0 by E magnitude times r 0 magnitude. Now, here the theta again in this case, as earlier we have discussed, that it lies between 360 degree, because in the plane of the orbit, if this is the orbital plane. So, your theta argument of perigee from the perigee line, it can lie from 0 to 360 degree. Okay. So, this condition is mentioned here. Now, then using this only you cannot resolve it, you need further condition, and this can be worked out if you look into the sign of this r dot v dot. Okay. So, if r dot v dot is greater than 0, then the theta is lying between 0 and 180 degree. And if r dot v dot is less than 0, then theta will be lying between 180 degree and 360 degree. So, we can put the boundary here like this, if we write 0 here. So, another we go up to this place, and from here to here we can write like this. Okay, now, what this exactly it is telling? This is your perigee position, and this is the r vector, r 0 vector, this is the angle theta, and velocity vector is in this direction. Okay, so, you can see that this is the, if r 0 is the vector in this direction. Okay. So, this is the angle here, and now as you keep going from this position. So, here if you look into this position. So, here this angle is 90 degree, then it increases. Okay. Thereafter, it will here figure is not correct, we will let me make it little fresh. This is the r 0 vector, and v 0 vector is lying in this direction. Okay. This is angle theta. So, at this position this is 90 degree. If you go here, you can see that this is getting reverted, r 0 will come here, r will come here, and v 0 will go in this direction. On the other hand, if you take this just opposite of this. So, r is here and v 0 is in this direction. So, from here it will be able to, you will be able to resolve this. If you take this r 0 dot product of r 0 and v 0, then you will get the exactly whether if it is greater than 0, then we write it that theta is between 0 and 180 degree, and if r dot v 0 this is less than 0, then it is a line between 180 and 360 degree, and you just reason it on the same basis as we have done earlier for the other angles. Okay, time is getting over. So, we do not have much time to elaborate further on this. So, we continue in the next lecture. Thank you very much.